we have our well-renowned Professor Scott Tremaine from IAS, who has a distinguished career in many astrophysical problems, especially the dynamics. And he has done many work that, including comets, spiral density waves, rings, and many things. So here we have the honor to have him give a talk on his recent endeavors. Thank you.
Okay, thank you. And my apologies for the delay. It seems that after 30 years of using PowerPoint and Keynote, there are still occasionally problems. What I'd like to talk about today is, now I have to advance this. Okay. Right. Going to talk about two particular subjects. One is what I've called the standard model for the formation and evolution of comets in the, particularly in the Oort cloud. And the second is an application of what we understand about the Oort cloud to try to discriminate models of modified gravity. So for the purposes of this talk, I'm not going to say much about the internal structure of comets. We can regard comets or cometary nuclei as pieces of ice and rock that are a few kilometers in size. The typical density is quite low. It's a fraction of a gram per cubic centimeter, which implies that comets are rubble piles with very little internal strength. That is, they're just accumulations of chunks of ice and rock with large amounts of vacant space inside. The typical mass of a comet, given the density and the size, is a few times 10 to the 16 grams. And they're believed to be leftover small bodies, sometimes called planetesimals, from the assembly of the planets in the outer parts of the solar system. These are images, all to the same scale, of half a dozen comets that have been visited by spacecraft. Although it's not important for the purposes of the talk, I want to stress that the interesting feature that many of these have an hourglass or dumbbell shape, that is having a smaller lobe and a distinct larger lobe. And you can see that here, you can see that here, you can see it with Halley's Comet here. And the details of why they have that particular shape are still an unresolved puzzle. The reason we see comets is that as they approach the sun, they start to evaporate material. As they evaporate material, they produce a coma, that is an optically thick atmosphere, and a tail of material streaming away from the comet. In fact, the comets produce two tails. There's a plasma tail, which is whose dynamics is governed by the solar wind, and there's a dust tail whose dynamics is dominated by a combination of solar gravity and radiation pressure. At large distances from the sun, before the comet starts to develop a tail and a coma, you're only seeing the comet by the reflected light from the nucleus, which implies that the brightness of the comet varies as 1 over r to the 4th, 2 powers of radius for the light to get out to the comet and 2 powers of radius for the light to come back. That means that it's extremely difficult to discover comets at large distances. There's an extremely strong selection effect against finding a comet a long way from the sun. And in fact, very few comets are discovered beyond distances of a few astronomical units. But that situation is going to improve with the Rubin Observatory, which will do a large survey for comets at much deeper magnitudes than we have so far. The other consequence of these sort of basic facts about comets, once the comet becomes visible, it can't survive for more than a few hundred orbits. It's only visible if it has a coma and a tail. If it has a coma and a tail, it's losing material rapidly, and that means that a typical comet on a highly eccentric orbit will come close to the sun, become visible, lose a lot of material, go away from the sun, settle down again, and that process will continue until the comet splits up or is completely evaporated and disappears. The other consequence of these basic facts about comets is that there has to be what I've called a cometary reservoir. Since the comets only last for a few hundred orbits once they become visible, there has to be some reservoir beyond a few astronomical units from the sun that's both stable enough to store the comets on timescales comparable to the age of the solar system, that is on gigayear timescales, but it can't be completely stable. It has to be somewhat leaky so that it's continually producing a slow stream of comets that become visible from the sun and then disappear within a few hundred orbits. And much of the motivation for, or much of the goal of trying to understand the origin of comets is to understand the nature of the cometary reservoir. Let me just briefly remind you of the basics of orbits in Keplerian potentials. All orbits, of course, are ellipses. The ellipse is specified by the semi-major axis and the eccentricity. The perihelion distance, the point of closest approach from the sun, which is semi-major axis times 1 minus the eccentricity. There's the inclination, which I'll always measure here relative to the plane of the planets. And there's the orbital period, and by Kepler's law, the square of the orbital period in years is the cube of the semi-major axis in astronomical units. The energy per unit mass is minus g times the solar mass over twice the semi-major axis. For simplicity, I'm going to set g to 1 and solar mass to 1 and 2 to 1 and minus 1 to 1 and call the energy just 1 over the semi-major axis. As a reminder of scale, the outermost known planet in the solar system is Neptune at 30 AU, and Proxima Centauri is at about 270,000 AU. Okay, so the best way to think about the origin of comets is to look at a plot of the distribution of orbital elements. This shows the inclination relative to the plane of the planets against the orbital period in years. There are many comets with very long orbital periods, and rather than leave them off this plot, they've all simply been plotted at an orbital period of 10 to the 5th years, which is the reason for this line of dots here. Apart from that, the most prominent feature is this cloud of cometary orbits at periods of less than about 20 years and at low inclinations. And that's the basic division in the distribution of comets. There's a cloud at low inclinations and small orbital periods, and another cloud with roughly isotropic distribution of inclinations and longer orbital periods. Because the comets' orbits are revolving as a result of interactions with the planets, but those interactions can't take an isotropic distribution and compress it into a flat distribution. That tells you that the short period comets, the ones in this clump, must have come from a reservoir that's a flat disk aligned with the planetary system. That was actually a theoretical prediction made in the 1980s, which was verified in the early 1990s when Jewett and Liu discovered the first object in the Kuiper belt, a belt of, or a disk of comets starting roughly at the orbit of Neptune and extending out to about 50 astronomical units. By now, since the 1990s, we've discovered several thousand objects in the Kuiper Belt. The Rubin Observatory is expected to discover another 100,000. And we believe that the Kuiper Belt out in this region is the origin of all of the comets in this, the short period comets in this clump of comets at small inclinations. The total mass of the Kuiper Belt is about 1/10 of an Earth mass. So this reservoir has to be somewhat leaky to produce the comets that we see, and we believe that it leaks as a combination of collisions between comets which change the orbits, non-gravitational forces on the comets, and weak orbital instabilities caused by the interactions with the planets. And those instabilities cause comet orbits to random walk or change in eccentricity until they cross Neptune's orbit. And then they have continued interactions with Neptune's orbit and the orbits of the other planets until they random walk down to sufficiently small orbital period and perihelion distance that they become visible in this cloud. The Kuiper Belt is a really important and interesting subject, but I'm not going to say more about it in this talk. I'm going to focus on the quite different problem of what the origin of the comets with an isotropic distribution is. In order to explore what this distribution is, the origin of this distribution, I'm going to make two changes. One is if I plot against orbital period, there are far too many comets at very large orbital periods to make a sensible plot with. So it's better to use the energy, or 1 over the semi-major axis, instead of the period, which goes like semi-major axis to the 3 halves. So I'll plot things against energy rather than against period. The second complication is that the comets that we see at a distance of a few AU or even smaller. And at those distances, the comets have already passed by all the giant planets. The giant planets exert gravitational forces which change the energy of the comets. And if you're going to investigate where the comet reservoir is, and it's outside the planetary system, you're better off using the energy that the comets had before they entered the planetary system. So all that means is that for each of these comets, you do a numerical integration of the orbit backwards, carry it past all the giant planets, past Neptune out to 50 astronomical units or so, and then calculate the energy at that point. Okay, so once you do that, this is a plot of what you get. This is the original energy, that is 1 over the original semi-major axis, the energy that the comets had before they entered the planetary system. The different numbers here correspond to semi-major axes of 1,000, 2,000, 10,000, and parabolic orbits. The first thing to notice is that there are a few hyperbolic orbits, but these are probably the result of observational errors or non-gravitational forces like outgassing from the comets when they come close to the sun. As far as we know, it's consistent with the distribution of errors to say that all of the comets that we see are bound to the solar system. The second thing to notice about this, of course, is the striking spike in the distribution of energies between a semi-major axis of about 10,000 AU and parabolic orbits. The existence of that spike tells you that there has to be a huge reservoir of comets, which has come to be called the Oort cloud, that are bound to the solar system at distances of typically 30,000 astronomical units from the sun, 10% of the distance to Alpha Centauri, and all of which are bound to the sun. One of the striking things to recognize about this is that the idea of the Oort cloud dates back to a paper by Oort in 1950, and the statistics that he had, instead of the 100 or so comets that we have in the Oort spike at the moment, he had less than about 10. So it's a reminder that in these days of big data, sometimes small data is sufficient to draw really interesting conclusions. The next question to ask, if you believe that there's this Oort cloud of comets at very large distance from the sun, the question is what happens to the comets after they come past the sun? As a comet travels through the solar system, the planetary system, in and out, it gets a typical kick in the energy of about 10 to the minus 3 inverse astronomical units, which is the size of this green arrow on the plot. So something that comes in from the Oort spike is typically either going to get a large random kick towards more positive energies in this direction, and it will show up somewhere in this tail of distribution of comets, or it'll get a kick in the other direction, in which case it'll be on an escape orbit and it'll be lost from the solar system and we'll never see it again. So this is basically a random walk in energy, which is analogous to the gambler's ruin problem, where you start off with a limited amount of money, you bet in an even game with a 50-50 chance of winning, and you ask how long you're going to survive until you become bankrupt, and the answer is that you'll survive for n orbits with a probability that goes like n to the minus a half. So you can ask if the simple version of the gambler's ruin problem correctly predicts the distribution of comets in this range here away from the Oort spike. And the answer is not quite. That in order to match the distribution of comets in this tail, you have to recognize the fact that comets fade with repeated passages close to the sun. They fade because they're losing their volatiles to the coma and the tail. And so you have to put in an empirical fading law, which says that the probability a comet will survive fading or physical disruption for n passages close to the sun goes roughly like n to the minus 0.6. So that physical process is certainly there, and with a plausible model for it, you can match the distribution of comets in this tail. You can say more about the Oort cloud. The Oort cloud is so large that kicks from passing stars and torques from the galactic tidal field are sufficient to randomize the distribution of orbits in the Oort cloud. In a statistical mechanical sense, it says that the distribution of comets on a constant energy surface in the Oort cloud is ergodic. It's uniform in phase space. And a consequence of that, if the distribution is completely ergodic, is that the fraction of comets with a perihelion less than some value q is just twice the ratio of q to the semi-major axis when the perihelion distance is small. So that's something you can test. This is the distribution of comets in the Oort cloud as a function of perihelion distance. This is linear, the blue curve is corresponds to a linear cumulative distribution, which is what you expect. It falls away from the uniform distribution simply because it's hard to detect comets when the perihelion distance is too large. Similarly, you can say something about the orientations. The fraction of, if the distribution is ergodic, the fraction of comets with an inclination less than some cosine of I is 1 plus cosine over 2. Again, you can plot that and for the Oort cloud, and you get a very good match. So it appears that the distribution of comets in the Oort cloud is basically ergodic. You can do more. You can estimate the total population in the Oort cloud. We know the rate of arrival of comets from the cloud with perihelion less than 1 AU is about 1 per year. We know the orbital period in the cloud. It's just given by Kepler's law. So at 30,000 AU, it's about 5 megayears. We know, since the distribution of comets in the cloud is ergodic, that the fraction of comets with a perihelion less than Q is 2Q over A. And so as a consequence of that, the number of comets in the cloud should be the rate at which we see new comets multiplied by the orbital period multiplied by 1 over the fraction that you expect with this very small perihelion distance. And if you work out the numbers, you get an estimate of 10 to the 11th comets in the Oort cloud. With a typical comet mass, given the size that I mentioned before, the total Oort cloud mass is about 1 Earth mass. The other thing I wanted to stress about this estimate is that since Oort only had 10 comets in the cloud, this estimate is an extrapolation of a factor of 10 to the 10th, which is pretty hard to do as in astronomy theory, but we still believe that this extrapolation is correct to within a factor of a few. So it's perhaps the biggest extrapolation that's been made in astronomy that turned out to be correct. Okay, you can say still more about the dynamics of comets in the Oort cloud, and but to say that, I want to switch away from the Oort cloud a minute to talk about stars and galactic nuclei. So in a typical galactic nucleus, you have a supermassive black hole surrounded by a cluster of stars. Encounters between stars in the cluster lead the velocities of the stars to random walk. And if the velocities random walk to a direction which is oriented too close to the black hole, the stars will come close enough to the black hole to be tidally disrupted. That means that there's what's called the loss cone in velocity space. There's a conical region in velocity space in which any star is going to be lost to the black hole within one orbital period. That is, it'll be lost to the black hole at the next pericenter. The reason this is relevant to comets is that all you have to do is replace the supermassive black hole with the sun, replace the star with a comet, replace the cluster of stars surrounding the supermassive black hole with the Oort cloud. Then again, encounters with passing stars in the solar neighborhood lead to a random walk in the velocity of the comet. If the radial component of the velocity is too small, there's a loss cone arising because the comets come close enough to the planetary system that they get an energy kick from from Jupiter or Saturn or one of the giant planets that's sufficient to remove them from the Oort cloud, either onto an escape orbit or onto a much more tightly bound orbit that is much smaller than the Oort cloud. So there's a loss cone that's exactly analogous to the loss cone that you see in galactic nuclei. The effect of the loss cone is quite an interesting one. Remember, you typically only see comets at very small perihelion distances. So here I've drawn a little circle, imagining that you're standing here looking down the loss cone. The comets are only going to be visible if their perihelion distance is less than a couple of astronomical units, but the size of the loss cone corresponds to a perihelion distance that's much larger. that's about 15 astronomical units. And then there are two flavors of dynamics that occur. If the kick from passing stars that the comet gets is small per orbit, it will random walk until it just enters the lost cone, and then it'll be lost either to an escape orbit or to a much smaller orbit. On the other hand, if the kick per orbital passage from passing stars is large enough, then in one orbit the comet can go from outside the lost cone into the region where it becomes visible, and we'll see it as a comet coming from the Oort cloud. That means that we only see the spike, the Oort spike, and the evidence for the Oort cloud if we're in this regime. If we're in this regime, you'd never know that the Oort cloud was present. So the conclusion from that, because we do see comets coming directly from the Oort cloud, that can only happen if the lost cone is full. The typical change in perihelion distance that you get per orbit is a strong function of the semi-major axis, because the tidal lever arm on the comet is proportional to the square of the semi-major axis, and because the orbital period is also larger. And so you can work out analytically that given the conditions in the solar neighborhood, the condition that the lost cone is full requires a semi-major axis that's bigger than about 35,000 astronomical units. That's, of course, exactly the size that you see for the Oort cloud, which says that we've successfully predicted the size of the Oort cloud with no free parameters. It also says that the size of the Oort cloud that we see is determined by the condition that the lost cone is full, and so the Oort cloud might and probably does extend to much smaller radii and have more comets than we think that it does. So far, I haven't said anything about the formation of the Oort cloud, but with this background, it's clear how the Oort cloud might have been formed. You start when the giant planets were fully formed, and you assume that planet formation was not 100% efficient, so that after the planets were formed, there were a large number of leftover small bodies, which we can treat as test particles on nearly circular, nearly coplanar orbits between the planets and outside the planets. We believe that the giant planets migrated early in the history of the solar system. As they migrate outward, they'll plow into the comets that are outside the planetary orbits and excite the eccentricities of the comets. The comets eventually random walk from repeated encounters with the planets to large eccentricities and semi-major axes, until eventually the kicks from passing the stars and the galactic tide change the orbits enough. They add enough angular momentum to the orbits so that the perihelion becomes large enough that it's outside the planetary orbits. They no longer get kicks from the planets. The semi-major axes freeze in place, and the comets join the Oort cloud. And once they're in the Oort cloud, the continued perturbations from passing stars occasionally bring them back to perihelion distances that are small enough where they become visible. So this is a story that I've told. The nice thing about the story is that you don't have to rely on believing me. You can calculate everything simply by doing long orbit integrations. You just set up a set of test particles, put in the giant planets, let them migrate for a while early in the history of the solar system, and then just follow the n-body problem involving the planets and the test particles for 5 gigayears and see what's left at the end. And this is an example of what happens when you do this calculation. The Oort cloud population shown here gradually rises as more and more comets random walk into the Oort cloud. but eventually, after a time of about a gigayear, the perturbations from passing stars are causing comets to evolve onto escape orbits, so the total population gradually declines. That's the total Oort cloud. What we see in the Oort spike is typically comets with a semi-major axis bigger than about 20,000 AU. There's also an inner cloud that's not visible to us, and you can see that the populations of the two are at the present time about equal. The line here is the population of comets that are in transit to the Oort cloud through this random walk caused by interactions with the planets, and that population is still present but rapidly decreasing as time goes on. For standard estimates of the mass of planetesimals in the left over after the formation of the planets, this tells you the efficiency at which they get placed into the Oort cloud, and the product of those two tells you the mass of the outer Oort cloud. It says that it should be about one Earth mass, which is what we estimated earlier in the talk. So there's a very nice agreement between the theoretical prediction of the mass of the outer Oort cloud and what we actually see. This is an independent calculation done a few years later. And in this case, the paper is plotting the eccentricity versus semi-major axis, the inclination versus semi-major axis. You can see that the comet cloud is roughly isotropically distributed once you get outside about 5,000 astronomical units. These are the comets that are still in transit. It occupies this particular locus because that's the locus at which the perihelion distance is in the region of the giant planets, so they're still getting kicked by perturbations with the giant planets. The inner edge of the Oort cloud is about a couple of thousand astronomical units, and the outer edge is about 100,000 astronomical units. What this still hasn't shown is that you can correctly reproduce the Oort spike. So you can plot things in terms of the inverse semi-major axis. The shaded histogram is the observed distribution of original inverse semi-major axes. Again, you can see a small fraction of comets on apparently hyperbolic orbits, but those are probably due to observational errors. Observational errors are sufficient that you should probably shrink this histogram a little bit. The colored histograms show the distribution coming from simulation of the formation of the Oort cloud. The different colors correspond to following the comets for a given number of orbits, presumably before they disappear or fade away. The blue is comets on their first orbit near the planets. The green is comets after 2 and 3 returns, and so forth. And you can see that if you allow for the fact that this distribution, the theoretical distribution, should be spread out a little bit to account for observational errors, and you assume that things fade after a handful of returns, you can do a very, very good job of reproducing the observations of the Oort spike. So I think everything holds together pretty well. There are uncertainties, but like the standard model in particle physics, this standard model for formation of comets does a very good job of reproducing most of the data. Okay, in the last few minutes, let me talk about one of the applications of the standard model, which is to testing a model of modified gravity. You've seen this plot before. It's just a plot that shows the distribution of comet inverse semi-major axes or energies with the Oort spike in it. And you remember I made the point that apart from a few comets that are probably subject to observational errors. There's this huge spike somewhere between parabolas and semi-major axes of about 10,000 astronomical units. So let's just imagine that gravity was described by a Yukawa potential. That is, instead of minus gm sun over r, you had an additional factor where of e to the minus r over the Compton wavelength of a particle of some mass m. Because of the presence of this extra factor, the escape energy for a comet from the solar system changes. And what I've plotted here is two arrows. One is the escape speed if the mass of the graviton is 0. This is the escape speed if the mass of the graviton is about 3 × 10 to the minus 23 electron volts. If this were true, then everything in the Oort spike would be on unbound orbits because it would have a gravitational energy that was bigger than the escape energy. That seems pretty unlikely, and so this gives a upper limit to the mass of the graviton. Now, just in comparison, there's a famous limit on the mass of the graviton arising from the LIGO observations of the binary neutron star merger, the fact that the gravitational waves arrived at the same time as the light from the merging neutron stars. That limit is actually weaker than the limit that you can get from the comets. So the limit from the comets have the potential to provide pretty strong limits on modifications to gravity. The particular theory of modified gravity I want to talk about is modified Newtonian dynamics. It's an attempt to eliminate the requirement for dark matter. As everybody knows, standard models in cosmology involve about 5 times as much dark matter as baryonic matter. And MOND replaces the dark matter with a breakdown in Newtonian gravity below a critical acceleration of about 10 to the minus 10 meters per second squared. MOND successfully explains a wide variety of phenomena on galactic scales, which I'll say a little bit about. So in particular, the place where MOND works the best is on looking for on explaining observations of dark matter in disk galaxies. In a disk galaxy, the observed stars and gas, that is the baryons, create a radial acceleration, which I've called G sub baryon. And in standard cosmology, the actual acceleration would be the baryonic acceleration plus the acceleration from the dark matter halo. In MOND, the actual acceleration is given by a quite different formula. It says that the acceleration is some function, dimensionless function of the total ratio of the total acceleration to this critical acceleration A0, and that this nonlinear relation relates the total acceleration to the baryonic acceleration. Now, what that means is that in contrast to standard cosmology, where the amount of dark matter can vary between galaxies, MOND predicts that the observed acceleration is a unique function of the baryonic acceleration. And that gives rise to a test of MOND called the radial acceleration relation. You simply plot the baryonic acceleration on one axis and the observed acceleration on the other axis. The baryonic acceleration is for disk galaxies is determined by adding up the acceleration from all the stars and gas that you see. The observed or total acceleration is obtained from centrifugal equilibrium and the rotation curve. And what you can see is that there is a very nearly unique relation between the two. The scatter away from the best fit relation is only about 0.15 dex, which is excellent by astronomical standards. And this is one of the classic pieces of evidence in favor of MOND. That is, it's making a prediction which is verified, which you can't make in dark matter cosmologies. The other consequence of this relation is that when the argument of this transition function is much less than 1, it's supposed to go like its argument. It's supposed to be a linear function of its argument. And if you plug that in, you find a relation that when the acceleration is weak, the observed acceleration should be the geometric mean of the critical acceleration and the acceleration due to the baryons. The acceleration of the baryons at large distances should go like gm over r squared. The consequence of that is that the expected asymptotic circular speed in a disk galaxy should go like the 1/4 power of the mass in baryons. And this is a plot of mass in baryons against asymptotic acceleration. And you can see that it's extremely well fit by the prediction of MOND. And once again, in dark matter cosmology, this is a feature that emerges from the details of star formation in dark matter halos, but it's not really a feature that's predicted in dark matter cosmologies. And of course, the other advantage of MOND is that it produces flat rotation curves without the need for dark matter. Again, in this typical case, this is what the rotation curve you would predict if you were in a Newtonian case with no dark matter, rotation curve decaying at large radii. And these other curves are what you predict with MOND. The MOND curves are a remarkably good fit given that they only have one free parameter, that free parameter being the stellar mass to light ratio. That's all I'll say about the phenomenological evidence for MOND, but there are huge reviews talking about the evidence pro and con. The description I've given so far is only valid for disk galaxies, and you'd like a more general formulation. The simplest and most elegant of these comes from a paper from Bekenstein and Milgram in 1984. Poisson's equation relating the gravitational potential and the density can be derived from a Lagrangian that looks like this. If you want to have a single potential rather than multiple potentials, then the most general modification of this is to replace the grad phi squared by a nonlinear function of grad phi squared to get a Lagrangian looking like that. And if you work out what the analog of Poisson's equation arriving from this Lagrangian is, it looks like this, where the standard Poisson's equation would just have mu equal to 1. So this is by far the simplest non-relativistic version of MOND.
Is that a kind of Klein-Gordon equation?
I'm sorry?
Is that a kind of Klein-Gordon equation in particle physics?
No, I don't think of it as a Klein-Gordon equation.
Or you call potential appears.
I'm sorry?
Okay, let's discuss later.
Okay. Okay, so once again, you've seen this plot before, and the point I want to make at this point is that if you're R out in the Oort cloud, the acceleration at 30,000 astronomical units is only about 5% of the MOND critical acceleration, and so it's in a regime where dynamics should be strongly modified by MOND, and it's natural to ask if the good results of the standard model persist if you replace Newtonian mechanics with MOND mechanics. And the best way to test this is to, again, look at the predictions for the Oort spike. This is the plot that I showed you before, showing the agreement between the a solid histogram, which is the observations, and the data. You spread the data out a little to account for observational error, and you allow the comets to fade after a handful of returns to the sun, and you get excellent agreement. So what we did was simply take the numerical calculations of the standard model and modify the calculations to replace Newtonian mechanics with MOND mechanics. That's more complicated than it sounds, but it's straightforward to do. There are no ambiguities in how it ought to be done if you believe in that Lagrangian formulation of MOND, and then you simply run the test particles for 5 billion years and see what the answer is. The answer looks like this. This is the Newtonian case again. This is the analog of the Oort spike for Mondian mechanics. Again, the solid histogram is the observations. The colored histograms are the results of running the standard model in MOND. And you can see that MOND fails badly. The Oort spike is too small, and the tail is too strong. And the presence of the tail is too strong, independent of what you choose for a fading law. So there's simply no fading law you can pick that will make the data agree with the theoretical calculations of the formation of the Oort cloud. So the conclusion from this is that MOND-based simulations can't reproduce the orbital distribution in the Oort spike. We've tried ways to get around this. We've changed the migration history of the giant planets. We've changed the migration history of the sun and the galaxy. We've played with various forms for the MOND transition function, looked at effects of the sun's birth cluster, different fading laws, non-gravitational forces, changes in the orbital acceleration, even a hypothetical Planet 9. None of those is sufficient to make MOND agree with the data. So we conclude that if MOND is the right theory of gravity, then this simple Lagrangian formulation can't be correct. There must be some change that is screening the effects of MOND either at small scales or small masses, that are masses and scales much less than the size and mass of galaxies. There are certainly other versions of MOND with a wide variety of names: tripotential MOND, Q-MOND, modified inertia theories, and so forth and so on. And we've looked at a little at all of these, and the problem is that they all either have many free parameters or they don't provide well-defined equations of motion, and so they're basically impossible to test. But we're ready and waiting if somebody can provide us with another theory of MOND and tell us that if this theory of MOND doesn't work for the comets, they'll stop believing in MOND, then we're happy to do the simulations over again. But so far, nobody has done that. So at least in the simple form, I think the comets provide persuasive evidence that this particular theory of modified gravity can't replace dark matter. Okay, I'll stop there. Thank you.
So we're open for questions.
You seem to have put a very high bar on the challenge that somebody must agree to you to give up MOND if their particular theory failed the test. Have you tried lowering that bar, saying you'll do it and they don't have to retract?
Yes, we have tried saying that, but then the trouble is if you say that, then the cost has gone from being very high to being zero, because they can always give us, send us an email saying, well, why don't you try this version of MOND? So we need a cost which is maybe lower than the bar we set, but higher than zero.
Anyone else? Please.
Is modified gravity due to some kind of dark matter or from the first principles itself? I do not understand why, for instance, Yucca potential appears for gravity theory. Well, for instance, in plasma theory, there are positive and negative charges, so they can shield the electric field, and by shielding occurs. So therefore, the potential can be described by the Yucca potential, for instance. Or in particle theory, in strong interaction, for instance, for bosons, and Klein-Gould equation gives the Yucca potential automatically, for instance. But I do not understand why the Yucca potential appears for the gravity theory, even in MOND. So,
sorry. So no, the Yukawa potential doesn't appear in MOND. I was only using that as an example of a simple modification of Poisson's equation that illustrated the sensitivity of the distribution of comets to changes in the basic law of gravity.
So I do not understand that point. To derive the Yucca potential, you need negative mass to screen the gravitational potential of individual massive object. Not necessarily. That is, I understand that's what the way that it arises in plasma physics, but you can also get it if you assign the graviton a non-zero mass. So okay. I did not imagine. I do not know the theory from so keep thinking.
Yeah. Next, you.
Yeah. So I think another challenge for the MOND theory is, of course, the CMB and the oscillation of peaks. Without that, the peak ratio, which is completely independent of the rotation curve. I'm just wondering, is there anything wrong with that argument, with the peak ratio argument, that allow people to think of MOND?
First of all, I don't want to get into defending MOND. Second, I agree with you that the agreement of the CMB power spectrum with models is an extremely strong argument for dark matter. The people who are advocates of MOND have claimed in the literature that they can reproduce the oscillations, the peaks in the CMB with a theory like MOND, but I've never read the paper with any care to see if I believe that it's correct.
That's not the simplest MOND that you're talking about.
No, it's not the simplest MOND that we're talking about. The other argument against any theory of modified gravity is that you need some sort of collisionless dark matter early in the history of cosmology, because if you don't, silk damping will eliminate all the perturbations before decoupling, and you won't have any perturbations left to build galaxies from. So there are good arguments, of course, for dark matter.
Let me put some words in slots more here. So the CMB, I'm a big fan of CMB here, but there I think the logical extension would be that MOND, the purists would say MOND is a description of a non-relativistic limit, and the extension to a relativistic theory, which is needed to even talk about the CMB or gravitational lensing or any of these, they well, that depends on the details of how you would extend it, and it's not really part of what these low velocity things test. But the comets are actually in the low velocity regime. Nothing is moving anywhere close to the speed of light. So you might think, even if you took, the 1983 paper, his prediction for comets would have been unique. Whereas in 1983, if you asked him, what you predict for the CMB, I'm sure he would have said, I don't know.
Yeah, that's correct. The CMB is a tougher test because it requires a relativistic theory. I mean, there are people who have alternative non-relativistic theories, but this is, as Whaley said, simpler because it's a non-relativistic case.
So you mentioned the outer Oort cloud is like 10% of the distance to South Centauri or something, where the tidal field probably should start becoming important, but do we know of any anisotropies of where the comets come from, depending on the direction towards?
You're correct that in principle you should be able to see anisotropies in the distribution of comets. Maybe not so much from Alpha Centauri because it's going by so fast that it doesn't affect the comets over the time it takes the comets to fall in. But you should see asymmetries arising, for example, from the galactic tide. The trouble is that, first of all, it's hard to. The trouble is that there's no uniform survey of comets. So what I was told is that the dominant uncertainty in the distribution of comets for a long time was that most of them were discovered by amateur astronomers in Japan, and in Japan it's rainy in the spring. So it's very hard to do anything without an unbiased sample, and hopefully that's something that the Rubin telescope will provide.
Okay, so back to galactic dynamics. What's your opinion about the result of the McNaught 2016? I mean, without MOND, if that's disproved, sort of.
Maybe you should tell me exactly which result you're.
It's kind acceleration is determined solely by the baryonic
right.
mass.
Yeah, that's one of the plots I showed earlier. What can I say? I think it's very impressive, and it's a definite prediction of MOND that dark matter theories can't predict, or at least can't predict without fine-tuning a lot of parameters having to do with the baryonic star formation. So I think it's a fascinating result, and I don't know what to say.
Okay, any other questions on comets? So what would you say of now if MOND's not correct? So where should we go back to right now?
Well, I don't think we've resolved the problem. The problem is that MOND does make dramatic and apparently correct predictions for disk galaxies. It doesn't do so well on scales of clusters of galaxies. It doesn't do well on scale of cosmology, and it doesn't do well on very small scales for comets. So I would say things are not looking good for MOND, but it's still doing an impressive job on the scale of disk galaxies.
Okay, very nice conclusion. Let's thank Scott.
Okay.